And welcome back to part 2 of our discussion of analysis of variance. You may remember in the last video I introduced an example study that we are going to walk through, and that study involved the different types of instructions for completing homework in statistics class. Specifically, one set of classes was given homework that was required. Another set of classes was given homework that was offered simply as extra credit, and a third group was just told that the homework was optional, it wouldn't help or hurt their grade, just do it if you want to. And then we measured how many of those students actually completed the assignments, and that's what the dependent variable was. So what I've got here are the data. Each row or each score represents the number of people in a class that completed the homework assignment. So I just circled the 5 classes who were in the required group, where it has so 22 students completed it in one class, 20 in another, 19 in another, and so on. All right, so that's the basic setup. And then I've given you the sum of x and the mean of each group. So let me clear the ink here. A little bit more about the setup here. You'll see on the slides in your lecture notes where I define terms like capital N, which is the total number of the entire experiment. In this case, that means that there were 15 classes total, whereas lowercase n is the number of individuals in each group. And there were, not individuals, but in this case, number of classes. And there were 5, 1, 2, 3, 4, 5 in each group. And then a new number or symbol that we're going to come across is K. And K is very simply the number of groups that are in the study. And in this case, K is 3. There were 3 groups, required, extra credit, and optional. All right, our first step in the ANOVA is we're going to calculate the sum of squares for the differences between groups. This is going to be the numerator of that ANOVA formula. Now, the theoretical formula for the sum of squares is n times the sum of the mean of each group, so of each group, minus the grand mean of the entire study squared. Okay. However, that's pretty complicated. I'm going to give you a simple version, and even this version that I'm going to show you is a little bit different than the version in your textbook. So this one I think is easier still. The formula for the sum of squares between groups, the computational formula, is once again n times the sum of x bar squared minus the sum of x bar quantity squared, let me make a better 2 of that, divided by k. All right, so what this means is we're going to take the mean of each group. So we had a mean here of 21, 14.8, and 6.6. Since we're looking at the variance between groups, that is how much each of these means varied from each other, those 3 scores are the x values for the sum of squares between. So what we have to do is square each of those and add them up, and that will give us this sum of x bar squared. And then we just sum them up and square that value. Notice how this formula looks very, very similar to the standard variance formula, the computational formula for variance. The only difference is, or at least it might feel a little odd at first, is that we use the means of each group as our scores instead of the individual scores. But other than that, it all remains the same. So, the other difference is the fact that we have to multiply by n. If you remember, n is the number of scores in each group. So in this case, that's 5. That's a real new concept that we haven't done before in any of our variance or standard deviation calculations. So make sure that you note that on your note card, because it will be important on the exams. And just trust me, we have to do that. We've got to multiply that answer by the number of scores that went into each group, the number of observations in each group. So completing the calculation, we had 5 was our n, and we're going to multiply that by, we have to add up all of the squared means. So we're going to square 21, we're going to add that to the square of 14.8, and we're going to add that to the square of 6.6. Okay, that's this right here. And then we're going to subtract from that the summing up 21 plus 14.8 plus 6.6. So we add up all of the means, and then we're going to have to square that and divide that whole thing by k. And if you remember, k is the number of groups that we have, so that would be 3. So take a second and work that out. Hopefully you paused the video and worked that out and came up with a sum of squares between groups equal to 521.735. If you didn't get that value, or something within a couple of thousandths of a decimal, just because of rounding, if you didn't get that, go back and double check your calculations and make sure you're using the means for your score. But that is the sum of squares between groups, the top half of the variance formula. We square each of the means and add them up, and subtract from that summed up means squared divided by the number of groups. Oh, and then, of course, remembering to multiply by 5 at the very end. That's going to be the stickler. That's where most people miss this question on exams. So make sure to remember to multiply by n. All right, that takes care of step 1 of calculating an ANOVA. So now we're going to do step 2 of that of the ANOVA, and this is where we calculate the sum of the squares within groups. Remember, the sum of the squares is just the top half of the variance formula, but we're breaking it down into different components instead of doing a variance of the entire data set. So the sum of squares within groups, if you look at the slides in the lecture notes, slide number 11 shows 2 different formulas for the sum of squares within. It shows a theoretical formula, which is the first one, and then what looks longer is more of a calculation-based one, and that's what I'm going to go over today. So to calculate the sum of squares within groups, we're pooling or adding together the variability within each of the 3 groups. So we're going to add the variability of those 5 scores to the variability of those 5 scores to the variability of those 5 scores. So clear ink. All right. And the formula for that is, so the sum of squares within groups is, first we sum up all of the squared values of group 1. We're going to add that to the sum of all of the squared values of group 2, and we're going to add that to the sum of all of the values, the squared values of group 3, and so on. If there were 4 groups, we would do, add 1 more, etc., etc. That's the first chunk, and then we're going to subtract from that the sum of all of the x's for group 1 squared divided by n for group 1 plus the sum of all of the x's squared for group 2,
And if it fits in there, the sum of all of the x's squared for group 3 divided by n. And that's it. That's it. So we're going to just square each of these numbers and then and add them up and then add up all of the individual scores. So if you think about it here, I mean, if I want to write it down, 22 squared is 484, 20 squared is 400, 19 squared is 361, and 17 squared is 289, and 27 squared is 729. So there we have our x and our x squared values. So if I add up all the x's, we already know we have 105, and if we add up the sum of x squared, we will get 2,263. And then if we did the next group here, we would get 1,110. And if we do this third group, square everything, we will get 235. That takes care of the first part, this part here. And then the second part, we're going to just take the sum of x, each of those scores. So we take 105. We're going to square that and divide by 5 because there are 5 people in group 1. We're going to add that to the 74 squared divided by 5 because there are 5 people in group 2. And we're going to add that to 33 squared divided by 5 because there are 5 people in group 3. And that takes care of the second part. And we just subtract that difference. And that in turn comes out to be 3608 minus 3518 over 90. That is our sum of squares within groups. That is the pooled variance, or sum of squares, the top part of the variability formula. The pooled sum of squares within each group. We're just taking those 3 groups and adding together, merging the variance within them. Alright, so that's part 2, sum of squares within groups. Now finally something very easily. We have to calculate the degrees of freedom between and within the 2 components of variance that we've calculated so far. Remember, this is just the bottom part of the variance formula where we typically divide by n minus 1. So between groups, degrees of freedom between is, that's between groups, is simply k minus 1. There are 1, 2, 3 groups, so 3 minus 1 equals 2. And then for degrees of freedom within groups, the formula for that is k times n minus 1. So there are 3 groups times, now lowercase n is the number of people in each group, and since the groups are all equal, it would just be 5 minus 1. 3 times 4 is 12. So we have 12 degrees of freedom within groups, 2 degrees of freedom between groups. And now we have calculated all parts of the variance formula. So what I've got on the screen here is the theoretical formula for variance. And if you look at the top portion there, that is just the sum of squares. We calculated one version of it for the difference between each group, where the x value was the mean, and then we created another value for the variability within groups, so we had to add it together because there were 3 groups. We added the within groups variability all together. The bottom portion of that formula are simply the degrees of freedom that we just calculated. So we've now done the top and the bottom part of the variance, well, two versions of variance. So let's put everything together and finish this ANOVA. So what I've got up on screen now is what's called an ANOVA summary table. And you'll have to do this on homework, so just pay attention to the columns. We have, the ANOVA summary table tells us the source of variability that we are measuring. There's either between groups variability, within groups variability, or total variability. Then we have the sum of squares that we calculated for between and within. We have the degrees of freedom, and then we'll get to those other parts in just a minute. A note about this total line, it's just adding up. That the total variability from one individual to the next in the experiment is made up of the variability due to our independent variable manipulation, what made the groups different, and the variability from one person to the next within each group. If we add those together, we'll get the total variability for everybody, the entire sample of 15 individuals. Okay, so let's fill this in. The next step after we calculate the degrees of freedom is to complete the mean square. And the mean square is just another name for variance. And if you remember, this is the top part of the variance, this is the bottom part of the variance. So all we have to do is divide. Where's there it is, divide. So 521.735 divided by 2 gives us 260.868. It's not showing up too well in there. For the within groups mean square, we have 90 divided by 12. 90 divided by 12 is 7.5. So there is our mean square between groups and our mean square within groups. In other words, the variance between groups and the variance within groups. The next step then is to calculate F. And the F ratio is between groups variability divided by within groups variability. In other words, we want to compare the variability between groups to the variability within groups. And if the null hypothesis is true, these two things are only measures of error. And error divided by error should be 1, or at least a very small number. If, however, the null hypothesis is false and our independent variable had an effect on behavior, then this between groups variability should be much larger than within groups variability. So that's the basic notion behind an F-test. If those two values are very similar, then we say, yeah, they're both measuring error. There's really nothing different about the two sources of variability. But if our IV has an effect, then between groups variability should be much larger. Similar to the t-test, where we took x bar minus x bar, the difference between two groups, and divided by that by the average variability between two groups. So we're taking the variance between groups and divided it by the average variability within groups. Anyway, 260.868 divided by 7.5 will give us 34.782. All right, so the ratio of the variability between groups to the variability within groups is 34.782. Another way of thinking about that is the variability between groups is 34.782 times larger than what we would see within groups. That seems pretty large. So the next step then is to just determine if this is significant. And that's going to require you to turn to table F, a new table in your textbook. And when you find that, this one's a little bit more complicated. But with an alpha of 0.05, we have to enter the table using our degrees of freedom. So along the top row, you'll see numbers for degrees of freedom in the numerator. and you'll see a 1, a 2, a 3, and a 4, and so on. Well, we had 2 degrees of freedom in our numerator, so that's where we're going to enter the table. And then down the left side, we have degrees of freedom for the denominator, and you'll see 1, 2, 3, dot, dot, dot. Well, we had 12 degrees of freedom in our denominator, so find 12. And where 12 and 2 intersect, we see 3.89. So 3.89 is our critical value. That's the point where any f value that's larger than that is one that would occur less than 0.05, because that is our alpha equals 0.05, or less than 5 times out of 100. Well, clearly 34.782, that's the value of our calculated f, is much larger than 3.89. Therefore, this is significant at the 0.05 level. And that is the end of the ANOVA. We now calculated a complete analysis of variance. We know that the different homework instructions caused a change in the completion rate among students. Unfortunately, all we know is that of the 3 groups in this particular experiment, at least one of them is judged to come from a different population than the others. They may all 3 come from different populations, only one of them. The problem is we don't know which, and ANOVA just tells us if the difference is greater than the differences among the means is greater than we would expect by chance, but we don't know exactly where that difference lies. So we have to go through one last process, and that is called post hoc tests. And I'm going to discuss post hoc tests and give the example in the next video. So you can go ahead and close this one up and open the next video up on post hocs.